Welcome to the Efficiency and Reliability Podcast. This is John, your host, and today's case study explores tackling tube coking and phase separation in vacuum unit heaters to improve operational efficiency and minimize downtime. Let's start. When planning a practical, functional, and cost-effective revamp, treating vacuum unit heater inlet through ejector outlet as a single system is essential. Nonetheless, process flow sheet models frequently fail to accurately depict the operation or address the numerous non-ideal conditions in a refinery vacuum unit. Under these circumstances, mistakes in calculating process stream data can lead to reduced operational durations, increased heat flux zones, tube coking, and low gas oil yields. A major challenge in processing crude feedstocks, particularly those derived from heavy alternative sources like bitumen, is tube coking. Coking, the formation of solid carbon deposits, is influenced by factors such as high temperatures, prolonged residence time, low flow velocities, and the diverse composition of the feedstock. The buildup of coke within the tubes not only reduces heat transfer efficiency, but also restricts flow, leading to increased pressure drop and potentially costly downtime for cleaning and maintenance. Therefore, mitigating tube coking is crucial for maintaining operational efficiency and profitability in refineries processing heavy feedstocks. The importance of considering phase separation in heater optimization. One example is how phase separation in the outlet vacuum heater tubes and transfer line affects the predicted heater outlet temperature and the estimated liquid flow rates in the wash section. Neglecting to consider phase separation in these lines can reduce the yield of gas oil products and lead to an excessively low flow rate of wash oil in the column. More critically, if this phenomenon occurs in the heater outlet tubes, it may cause tube overheating in vapor-only regions with low heat transfer coefficient, causing the actual tube metal temperature to approach the design metal temperature. For this scenario, it is not only a question of underestimating wash rate and overestimating gas oil yield, but safety. Most conventional modeling practices assume liquid and vapor equilibrium at the vacuum heater outlet, even for these large diameter horizontal tubes. Still, in reality, especially after lowering the initial vacuum column pressure, liquid and vapor phases tend to separate even before entering the transfer line. Calculated phase regimes are either stratified or stratified wavy. Stratified phases cause the liquid and vapor to have poor mass and energy exchange across the interface, resulting in poor liquid and vapor contact. So phase separation causes the vapor to flow through the top of the horizontal portion of roof tubes, and this vapor becomes superheated due to pressure reduction. The upper part of the tubes doesn't see a flame, so it is not subject to any significant oxidation scale formation. Keeping that in mind, the sizable gap between the actual process outlet temperature and tube metal temperature greater than 200 degrees Celsius can be encountered, way exceeding the best design practices of no more than 80 degrees Celsius or a maximum TMTMT of 500 degrees Celsius. An energy company contacted the IGS thermal efficiency team to design a solution to tackle the tube coking issue, since numerous attempts to adjust the operational regime had no success. The internal investigations also didn't result in any solution that would avoid costly revamps during the upcoming shutdown. The large OD outlet roof tubes within the vacuum heater outlet tubes reduced mass velocity, resulting in liquid and gas phase separation. This caused hot spots due to the lower heat transfer coefficient inside the top portion of the roof tubes. IGS recommended that proprietary ceramic wrapping technology be used to cover the 180-degree circumferential surface of 8 inches and 10 inches top roof tubes, along with IGS proprietary technology to secure material on top of the tube surface. The objective of this project, according to the IGS evaluation, was to reduce heat flux from approximately 11,000 to 1,150 British thermal units per square foot per hour with a 190 degrees Celsius tube wall temperature drop. Entirely removing tube coking hotspots on the top part of these 8 inches and 10 inches tubes, the IGS operations team successfully completed all work within the heater over a 3-shift period, finishing on time and within budget while prioritizing safety as their foremost principle. Skin thermocouple readings were also analyzed before and after the project. The expected tube wall temperature reduction was confirmed with the data following the project execution: 596 degrees Celsius versus 416 degrees Celsius. At the same time, due to the lowering of the available area for heat transfer only for the low HTC region, the flue gas temperature entering the convection section increased by only 12 degrees Celsius on average without the increase in stack temperature. The coked vacuum heater tubes were debottlenecked without any penalty in terms of efficiency, allowing additional throughput for the vacuum unit and downstream facilities without any TMT-related issues. And that's it for today's episode. Thanks for joining us. To learn more about this project and other case studies, please visit our website at www.integratedglobal.com. Don't forget to like and share and subscribe to this podcast.